We're going to switch topics, and we've spent quite a little bit of time looking at combustion reactions. We're now just going to look at some of the thermal effects. And so while the air around us, or the environment in which we live in an environment where the temperature ranges from about minus 40 degrees Celsius this past weekend to plus 40 degrees Celsius 10 months from now. We'll get to it, all of us together. We know that water melts at 0 degrees Celsius and it boils at 100 degrees Celsius, but the environment around us, even the air, if we cool it down enough, we will eventually liquefy the nitrogen, oxygen, and all of the components in the air. And for example, we have liquid nitrogen right now, and that liquid nitrogen is at?
Minus 196 degrees Celsius. So I think the lowest temperature on Earth is probably about minus 82. So to get this sort of temperature, you're looking at being on the International Space Station, going out for a spacewalk. And yeah, minus 196. Well, let's just have a quick look at it. So here it is here. What's happening is water that is around us is actually forming little mists or clouds. And if the water actually touches the cup, we're actually getting snow and ice forming. It really isn't bubbling that much. I mean, it should be boiling vigorously like soup on a stove. However, because this cup is very smooth, you don't get much bubbling occurring in here. I don't know if you can see it, it's just a little. I'm going to change the container here, and we'll go over to a glove. This glove is, that's a different material, but if we place that in there, maybe I'll add a little more, you'll see that there's quite a bit more bubbling that's occurring here. Right? So that's what soup on a stove would look like if it were 220 degrees Celsius above water's boiling point. Well, at least the element here. Now, materials will behave differently at low temperature. We'll just pour this out here, and we'll show you that it looks like it's unharmed, but we should realize that materials behave quite a bit differently. On an International Space Station walk, you definitely need better materials than we have here on Earth, right? NASA actually comes up with special formulations in order to allow us to be able to go on spacewalks and be able to conduct research outside. Maybe I'll end off with showing you that everything here is very hot. This table is 220 degrees above its boiling point. We'll pour some on and you'll see, like a hot frying pan, you can see that it's sizzling on our surface here and evaporating. All right, I will stop it at that point there. Thank you.
You don't need to get to minus 196 to get to see something go brittle. You don't need to get to minus 196 degrees to see something go brittle. Actually, the next time you get a really nice good cold snap around here in Edmonton, go outside for a reasonably long walk with a nylon jacket on, and as you're walking down, as long as you're not listening to an iPod and chatting with your friend, but nice quiet walk along, and all of a sudden you start hearing crack, 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 like the fibers in your jacket are breaking. Well, they actually are, because nylon goes brittle at around minus 25 degrees, depending on the actual formulation. So it's not a surprise that elbows, shoulders, and the knees on ski pants are where the fibers break the quickest. They're the most moved, and if you're in really cold temperatures, the most brittle, and so they start cracking.